We're going to look at related rates here, and this is kind of the most kind of significant chunk from this unit. So this is one to really focus in on. And the idea that we're looking at is if there's two quantities that are related, what does that mean for their rates? How are those related? So jumping into this, by definition, two rates are considered related if the numerator of the rates are related with an equation, and if the denominator of the rates is the same. So in other words, if you have two quantities that are related, like for example, the radius of a circle and its area, and then you take both of the derivative of both of those quantities with respect to the same thing, for example, time, those are related rates. So another example would be the height of the water and the volume of water in a bucket. So if you imagine a nice bucket, we'll make it simple, make it a cylinder. Well, the height of the water, right, the height here, and the volume, well, the volume is equal to pi r squared, which is, the area of the base, times however high you are. So we can relate volume and height, and then as time goes on, as that fills up, you might imagine a dV by dt and a dH by dt. So if we took the derivative of height with respect to time, took the derivative of volume with respect to time, these two would be related rates because the numerator, this v and this h, are related, and they have the same quantity here in the denominator. The easier way to think about it, perhaps, is just imagine you have an equation that relates two values, two quantities, and then if you take the equation, the derivative of that with respect to time, all the rates that show up, or if it's respect to something else, all the rates that show up in that equation are now related rates. So here's an example problem. You're filling a balloon, you want to know how quickly the radius is changing when it's 6 centimeters large. Unfortunately, it's logistically impossible to measure the radius of the balloon directly, right? Because you can't get something into the center. Luckily, you know that you're adding exactly 10 cubic centimeters of air per second from the tank that you're using. And so the question is, how quickly is that radius changing? Well, let's start by writing an equation that relates the radius to the volume, because we're adding 10 cubic centimeters of air per second. So that's a volume. So the volume of a sphere is 4/3 pi r cubed. So now we can see that we're relating the volume and the radius. So now we're going to take the derivative with respect to time because we want to find how quickly this radius is changing. So dV by dt will be on the left side. And then on the right side, I'm going to write this out so we can kind of talk through what I'm doing. Okay, 4/3 pi, that's all, constants. So we have dV by dt is equal to 4/3 pi. Then we have the derivative of radius with respect to time. Well, that's going to be 3r squared because, the derivative of r cubed is 3r squared. But then because we're asking about with respect to time, not radius, we need to use the chain rule and get our dr by dt. And now what you'll notice is we have a relationship between dv dt and dr dt. That relationship is dv dt is equal to 4 pi 3r squared dr dt. Well, we want to solve for dr dt, so we'll solve for that by isolating it. And I'm just going to be lazy and just throw this kind of mess into the denominator here. And now the question is, what can we plug in? So we're going to have dr by dt is equal to 1 over 4/3 pi times 3, and the radius we want to know when it was 6 centimeters. So 3 times 6 centimeters squared. And dv dt we said was 10 centimeters cubed per second. So if you do all this math out, work out your units, blah, 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 I'll leave that as an exercise for you to work with. You should see that you get about 0.044 centimeters per second. And that's just from, again, plugging in all these numbers, running it. And then you'll notice that we have centimeters cubed in the numerator, centimeters squared in the denominator. That leaves us with centimeters. We have seconds in the denominator. And this makes sense because it's telling us how big, how much that radius is changing, which should be measured in centimeters, and we should be looking for how quickly it changes every second. So this is an example. Let's summarize how that kind of all comes together. So first, write an equation relating both quantities, the two things you want to find the related rates of. It might be more than that, but for the most part in this class we're going to look at 2. Then take the derivative of the equation. Don't forget to use the chain rule. Then algebraically isolate the rate of interest, so whichever one you cared about. And then finally substitute in the known values. And that will, basically end up giving you an expression that tells you what the rate is that you're wanting to find. So this is what we look at for the overview of related rates. Of course, if you have questions, feel free to ask, but in the next video, we'll look at a couple more examples.